All right. So today I want to talk about the major two. Actually, next week you have a major two, and major two, similar to major one, it consists of two parts. Part one include multiple choice questions, and I will share and discuss several similar questions with you in the WhatsApp group. But regarding for part two. You will have three questions from the following lectures, lecture 8, 9, and 11. Let me add a new student. And I have already solved these similar questions for you in the class before, but however, I would still like to review them with you again today because they are very similar to um, uh, major the questions in major two. So, well, the first question is from lecture 8, and we will talk. We will take a look at together. One second to add. All right, this is the first question. This examples from lecture 8 reviews the voltage distribution across a string of three insulators, as you can see in this figure, in 33 kilovolt overhead transmission lines. The key idea is that due to the presence of shunt capacitance between each insulator pin and earth, you can see here, these are shunt capacitance, um, given as 11% of the self-capacitance. So we have this value here. So each of these shunt capacitance are 11% of the self-capacitance. We call this one self-capacitance and this capacitance as a shunt capacitance. So the voltage is not evenly distributed across the disks. So each of these voltages are completely different. So and instead, the disk closest to the conductor experiences the highest voltage stress. It means this one. This insulator is closest to the conductor, so we have a highest voltage here, V3. This is highest voltage one, while the top unit it has a lowest voltage. So using an equivalent capacitive model, the voltage deviation is derived step by step at each junction, showing how the coupling effect increases the voltage from the top unit V1 to the bottom unit V3. So let me, okay. And we have this capacitor, this factor. This is a shunt capacitance factor. So shunt capacitance divided by self capacitance is equal to K, and voltage across a string. We are in three phase. We have a three phase, so it should be divided by a square 3. So we will have phase to natural voltage here. So at junction A, if we can write KCL in this junction, I2 is equal to I1 plus I1. So this voltage is V2. So again, Ohm law V2Z, so omega C is equal to this voltage is V1. So and these 2 points are connected together. So this voltage also is equal to V1 is equal to V1 CW plus V1 KCW. So this is the capacity, shunt capacitance is equal to KC. So after you can just taking the V1 in the second side of the equations, we will have this relation. So the analysis leads to an unequal distribution V2 and V3 being progressively higher than V1, which highlight the importance of grading or design improvements in real transmission systems. We will see in the following examples how grading is working. And finally, the concept of so we can find again we can write another KCL here at junction B. So we have I3 is equal to the summation of the current going out from this node. I3 is equal to I2 plus I2. So I3 is equal to V3 omega C is equal to this one is V2 C omega plus. So what is this voltage? This is a V2, this is a V1. So we can write a KVL here. The voltage across this capacitor is equal to V2 plus V1. So times Kc omega. So after that, we will have these two equations. V2 is equal to 1.11 V1, V3 is equal to 1.342 V1. And so V is equal to V1 plus V2 and plus V3, right? We have this equation as well. This is a KVL. We can just replace the values in these equations, and finally V has been calculated based on this information. So V1 can be voltage across top unit is equal to this value. And if we can find the V1, so then we can find V2 and V3 based on the previous equations. And as you know, the string efficiency is equal to voltage across a string divided by number of the insulators times the maximum value of the voltage, the V3. So is equal to 85.8%, and which indicates the degree of voltage imbalance in this system. So we have this voltage imbalance in the systems. This slide introduces another example of three-phase transmission line supported by a string of three-disc insulators. The key objective here is to analyze the effect of shunt capacitance on voltage distribution along this string. So given that the voltages across the top and middle units are this voltage and this one are 8 kilovolt and 11 kilovolt respectively, and we can by using of Kirchhoff current law can be applied in these two nodes, and this leads to the determination of after that we can find actually the capacitance ratio, which is equal to K, and which represent the ratio of shunt capacitance of self-capacitance. So the equivalent circuit shown helps visualize the current path and capacitive effects, forming the basis for further calculations of voltage distribution and string performance. The rest of the formulations are equal to the previous example. At junction A, we can write I2 is equal to I1 plus I1. Again, this voltage is V2 CW is equal to V1 CW plus V1 again KCW. So K can be calculated based on this. We know about V2 and V1 and so on, so we can just replace the values. And Kirchhoff current law at junction B is equal to I3 is equal to I2 plus I2. This one is a V3 CW is equal to V2 CW plus. What is this voltage? This one is V3, and so I2 is equal to just KVL here. This is V2, this is V1, so V1 plus V2. So, and V is equal to V1 plus V2 plus V3. We have another equations like this. So we know about K, we know about the V1, V2, so we can find V3, and then we can substitute in this equation. We can finally find voltage between line and earth. And the line voltage in three-phase system is equal to square 3 times this voltage. And string efficiency can be found again based on these equations, and we will have 68.28%. Okay, so this is another example. Uh, I just try to solve again all of the examples because these examples are very, very similar to your to one of your questions. Okay, this slide present a new example of a three-phase system where each line is supported by a string of three identical insulators. You can see here, considering the effect of shunt capacitance. So we have a shunt capacitance. So in this case, the shunt capacitance is assumed to be 1/8 of the self capacitance, resulting in K is equal to 0.125. So starting from the given voltage across the line unit, it means V3. We know about this voltage is equal to 17.5 kilovolt. So we can write the Kirchhoff current law at junction A and B, similar to the previous one. So we will have these two relationship, V2 and V3. So uh, we know about V3, so we can find V1, and then we can put it here, and we can find the V2. So the total voltage between line and earth is equal to V1 plus V2, and V3 is equal to this one. And then we can replace in the string efficiency equations, and we can find the value. So finally the string efficiency is found to be 84.28%, indicating a relatively improved voltage distribution along the insulator. So here in this case. Okay, this is another example. This slide present an example of voltage distribution across a string of post-type insulators in an outdoor substation. So each unit consists of 3-pin type insulator. So here, yeah, 3-pin type insulator, where each unit has a safe working voltage of 15 kilovolt. And due to the presence of shunt capacitance, the voltage distribution across the unit is not non-uniform. So with the maximum voltage appearing across the lowest unit, and the ratio of self capacitance to shunt capacitance is given by 8 to 1, leading to a capacitance ratio factor K is equal to 0.125. By applying again Kirchhoff current law at the junctions, relationship between the voltage across each unit can be derived. So we can just replace the values in the equations. And solving these equations shows that the middle unit has a voltage of um, V2. V2 is a middle unit voltage of um, 12 point 12 point yeah, V2 V3 here. V2 is 12.13 kilovolt, and V1 then can be calculated based on this. So we can just put it here, so we can find V1, and finally voltage across this string, and V3 is equal to this one, so we can put the value of V2 here again. We can find V3, and finally the voltage across the string is equal to this one, and then we can find the string efficiency. So the string efficiency is around 84.26 percent, indicating how effectively an insulator string utilizes its total voltage rating despite the unequal voltage distribution between the insulators. Okay, this is another question. This slide explains the voltage distribution across a string of four suspension insulators when the self-capacitance of each insulator is 10 times the shunt capacitance to earth. To simplify the analysis, the equivalent reactance method is used for. So we have a four insulator here. So by assuming the self-capacitance reactance at as a 1 ohm and the shunt capacitance reactance at 10 ohm. So we have these two values. Starting from the top unit, the current through each insulator increases progressively because of the additional shunt currents here. So following through the capacitance to earth. As a result, the voltage across each disk is not uniform, similar to the previous one. So the calculated voltages at 1 volt, 1.10 volt, and 1.31 volt, and 1.65 volt from the top unit to the bottom unit, respectively, from here to here. So giving a total string voltage of 5.606 volt. So this slide also shows the percentage voltage distribution across the insulator. Very easy, you can just write the percentage. So 1 volt over the 5.606 volt, it means that 19.76 voltage will be drop on the top unit, and so on. So the bottom unit experiences the highest voltage stress at about 32.6%, while the top unit carries the only about 19.76% of the total voltage. Finally, the string efficiency can be calculated as 76.6%, demonstrating that unequal voltage distribution always reduces the effectiveness of the insulator string, and the highest importance of improving voltage grading in high voltage transmission systems. Okay, this is another question. As I told you, we can use grading then in order to increase the string efficiency. So this slide presents the analysis of three-unit suspension insulator string, considering the effects of self-capacitance, shunt capacitance to earth, and capacitance to the transmission line. Each insulator has a self-capacitance of C, you can see, while the shunt capacitance to earth is equal to 0.15 C. It means that 50% of the self-capacitance, and the capacitance to the line is equal to 10% of the self-capacitance. And this figure illustrates the physical arrangement of the insulator string, and then shows its equivalent electrical circuit used to for analysis. Because the capacitance connected to the earth and line created additional charging current, the current through each insulator unit is different, so leading to a non-uniform voltage distribution across the string. So I'm just trying to repeat every time what is the physics behind these examples. The voltages across the three insulator units are represented as V1, V2, and V3, where the unit nearest to the conductor experiences the highest voltage stress. We will find later. And this unequal distribution reduces the overall performance of the string and affects its string efficiency. In general, this example demonstrates how capacitance affects influence voltage grading in suspension insulators and emphasizes the need for methods such as grading rings or capacitance control to improve voltage uniformity and increase the insulation reliability in high voltage transmission lines. So this slide explain the voltage distribution and the solution for the example. So here again we have to write a KCL for these two junction. So I2 is equal to I2 plus I1 prime is equal to I1 plus I1. So this one is a V2 CW plus I prime 1 here. So this junction is connected to this junction. The voltage from this point to this point is equal to V2 plus V3, right? So the voltage between these two nodes is equal to V2 plus V3. So V2 plus V3 times 0.1 CW is equal to I1. I1 is a C1 V1 CW V1 CW plus I1. So I1, this point, this node are connected here together, and these two nodes are the same. So the voltage here also is V1. So V1 0.15 CW. And again, for junction B, KCL here is equal to I3 plus I prime 2 is equal to I2 plus I2 V3 CW plus this voltage. So this voltage is equal to V3 because these 2 points are the same, right? V3 0.1 CW is equal to I2 V2 CW plus so from here to here is equal to V3 I2 here. So what is the voltage of I2 is equal to I2 from here to here. So is equal to V1 plus V2, right? Because these two nodes are connected together. So voltage from here to here is equal to V1 plus V2. You can use this way, but this one is so easier. So times CW times 0.15. So we will have these two Kirchhoff current law, and then we have so putting the value of V2 from expression 3 into the expression 1. So here V2 we can put it here. So we will have a V3 based on these equations. Let me add a new student. Okay. and also V1 plus V3, V2 plus V3 is equal to V. So we can uh, put all of values here. Just we can have V based on V1. So V is equal to V1 is equal to V1 is equal to this one times V divided by 440.55. So what is V? Uh, the total voltage is equal to uh, 1, right? Yes, we can we can put the total voltage, yes, is equal to uh, yes, we divided by V, so V1, yes, is equal to 1, and we can replace the value here, and we can find the V1, V2, and V3. So the top unit uh, consuming 32.6% of the total voltage, and the medium unit 30.7%, and the third unit is consuming maximum voltage 36.4%. So finally, string efficiency is equal to can be equal to 91.5. So you can see that by adding a grading, we can increase the string efficiency. So uh, this is a very important analysis in high voltage transmission system to ensure reliable insulation performance and reduce the risk of flashover. We discussed in more detail what will be happen if we increase the string efficiency, and how we can reduce the risk of flashover in transmission line. Okay, this is another example present the effect of using a guard ring again on the voltage distribution and string efficiency of the 3-unit suspension insulator string in a 3-phase transmission system. By increasing the capacitance between the line and the lowest insulator unit from 0.1 C to 0.3 C, the guard ring helps equalize the voltage across the insulator units. So we want to see what will happen. So we increase the capacitor 3 times, So applying the Kirchhoff current law again in these two junctions, and replacing all of values. So voltage between the conductor and the earth, V total V is equal to 3.07 V1. So, and the V3 is the maximum value. We can put it here. We have a 3 insulator, so the number of insulator here is equal to 0. And finally, you can see that the string efficiency is even better, So demonstrating that the guard ring effectively reduces the unequal voltage stress, and enhances the reliability of high voltage insulation systems. Okay, in this section, I would like to review a few questions from lecture 9 once again here. So this is a first example. It's very similar to one of questions in major 2. So you can see that we already discussed about if there is a difference between the height of the towers, how we can how the sag points can be moved, And this slide illustrates the sag analysis of the transmission line crossing a water body between the two towers of unequal heights. You can see that we have unequal heights between these two towers. The conductor is supported by towers of 30 meter and 90 meter with a horizontal span of 500 meter. So using the given conductor tension and weight per meter, the problem evaluates the shape of the conductor curve and determines the minimum clearance above the water surface as well as the clearance at the midpoint between the supports. It means that we want to find this one and this one, this point. This is a medium point. It means that from here to here is equal to 250, and from here to here is equal to 250. And this is actually, we want to find the sags at point O as well. So this figure shows the lowest point of conductor, the sag distance, and the geometric relationships used in the calculation. So this type of analysis, as I told you, is essential in transmission line design to ensure adequate ground or water clearance, maintain mechanical safety, and satisfy electrical installations requirements under um, uh, different operating conditions. All right. So let's have a look at to the solution. So we can find the edge because we have 8 of the tallest tower, so is equal to 19 minus 30 is equal to 60. So h is equal to 60, right? So and the lowest point is O. Uh, O is of the conductor, lowest point of conductor. So assume that this is a x1 and the midpoint is here P. So the difference, the distance between P and O, we can assume that this is a x. If this is a x1, this is a x2, x1 plus x2 is equal to 500. So we have this first equation. So sag SF1 is equal to Wx1 power 2 over 2t, and sag SF2 is equal to Wx2 um, power 2 divided by 2t. And this h is equal, this is a S1 from here to here, this point. This is regarding the tower, the smallest tower, S1 from here to here, O. So H is equal to, again, S2 minus S1, right? This is S1, this is S2. So H is equal to S2 minus S1, and we have two equation for S1 and S2. We can put it here. So x2 power 2 minus x1 power 2 is equal to x2 plus x1 times x2 minus x1, right? X2 plus x1 is equal to 500 from here to here, the distance between two towers. So x2 minus x1 can be calculated 256. So we have two equations, two variables. X1 plus x2 is equal to 500, x2 minus x1 is equal to 252. So if we can sum these two equations together, x1 and x1 can be removed from this side, so we can find the x2, and then we can put in one of these two equations, we can find x1. So if we have x1 and x2, S1 and S2 can be calculated very easy. S1 is a weight times x1 power 2 over 2t. So uh, t is also is equal to uh, 1600 kilograms. So this is tension. Clearance of the lowest point. So here, this is a 30 meter from here to here. So S1 from this point to here is 7 meter. So 30 meter minus 7 meter is equal to 23 meter. And I want to find X. I want to find the S here, sag at midpoint. So sag at midpoint is equal to W X over power 2 divided by 2t, right? So how can I find the X? X is here. From this point to here is equal to 250, right? We find x1 from here, so 250, no, let me, um, yes, 250, and x1 is equal to 122 meter, right? So we can find x, and then we can replace here s sag at midpoint p can be calculated. So very easy. You can also find sag from this side if you assume this distance, but this one is so easier. Clearance of midpoint P from water level, so from here to here. From here to here, S1 is equal to 7 meter. From here to here, so from here to here is equal from here to here is equal to 23 meter, right? And S1 is equal to uh, 23 meter, and yes, sag in this uh, in this point from here to here, the total sag is equal to 7.68 minus the clearance from here to here, 20 plus the 23 is equal to, in total will be 30.68 from here to water. So this example also demonstrates the practical application of sag calculation in transmission line design to ensure adequate ground and water clearance for safe operation. So the questions in Major 2 just has some difference in the values. The rest of things are similar. So the methods are similar for both of examples. So this is another example explain the sag analysis of an overhead transmission line conductor suspended between two supports at different deviations. Again, we have two deviation here between these two towers. The conductor has a parabolic configuration. You can see this is a parabolic curve with a weight of 1.925 kilogram per meter of length, while additional ice loading of 1 kilogram per meter is considered, and wind pressure has been neglected. So the span length between supports is 600 meter between these two supports, and with a height difference of 50 meters. So h is equal to 50 meters. Using the conductor cross-sectional area and ultimate tensile strength, the the allowable tension is determined based on a safety factor of 5. This figure illustrates the unequal sag conditions on both sides of the lowest point of the conductor, represented by S1 and S2, and horizontal distances x1 and x2. This example also highlights the importance of the mechanical design calculation in transmission lines to ensure safe conductor tension, adequate ground clearance, and reliable operation under leading conditions such as ice accumulation and so on. So x1 plus x2 is equal to 600, h is equal to this one, the height of support B minus the height of support A. So let's have a look at the solution. Similar to the previous one, so L is equal to 600 meter, Wi is one ice is equal to 1 kilogram, H is equal to 50 meter, W is equal to 1.925 kilogram, T is equal to 1000 times 2.2 divided by 5 is equal to 3520 kilogram. So total weight of 1 meter length of conductor is equal to Wt is equal to W plus W weight of ice. So in total, we will have this weight. So we wanna find the lowest point is O. So from here is we can assume that this is x1 and x2. x1 and x2, x1 plus x2 is equal to 600 meter. So h is equal to this h is equal to S2 from for this support from B to O, and S1 minus S1 from A to O point. So just we can use these two equations, and then x2 power 2 minus x1 power 2 is equal to x2 plus x1 times x2 minus x1. So x2 minus x1 is equal to 50 meter. We have two equations, two variable. So x1 and x2 can be calculated, and then we can uh, put it in one of these two equations. We can find the S2 and S1. So sag from the taller of the two towers is equal to S2 is equal to 45.24 meters. So this example demonstrates how conductor loading support height difference and allowable tension influence sag calculations in overhead transmission line design. So let's let's have a look in a few questions from lectures 11. So in lecture 11, uh, we found some questions regarding capacitance of underground cable, right? So this slide presents an example of calculating the capacitance of a single core cable. The conductor diameter is 1 centimeter, while the internal sheath diameter is equal to 1.8 centimeter, and insulation material uh, uh, is impregnated paper with a relative permeability of 4. Using the standard capacitance formulations, so for cables, the capacitance can be determined 0.378 microfarad. So by substituting the given values to these equations, we can find this value. So this example demonstrate how cable geometry and insulation properties directly influence the capacitance of underground power cables. So this is one example. This is another example explain the calculation of capacitance and charging current for a single core cable operating in a three-phase 66 kilovolt power system. The cable is 1 kilometer long with a core diameter of 10 centimeter and insulation thickness of 7 centimeter using the relative permeability of 4 and the standard cable capacitance formula. The capacitance can be calculated as 0.254 microfarad. So after determining the phase voltage between the core and sheath, the sharing current is obtained using the capacitive reactance relationship at a frequency of 50 Hz. So the final charging current can be calculated as 3.04 amp. This example highlights the importance of cable capacitance in HV transmission systems and high voltage transmission system and its effect on charging current. So this is uh, these three examples are the introduction to the main questions. I will let you know. So this is a slide also demonstrate the calculation of capacitance, charging current, and total charging reactive power for a 33 kilovolt three-phase underground cable system. The system uses three single-core cable, each having a conductor diameter of 2.5 centimeter and insulation thickness of 0.5 centimeter over cable length of 4 kilometer. Using the cable capacitance formula and relative permeability of 3, the capacitance per phase can be calculated as 1984 times 10 power uh, this nanofarad. So the phase voltage is then determined from the line voltage and the current. Very easy, we can find the phase voltage. And the charging current per phase can be obtained um, as 11.87 amp using the capacitive current equations. We know about that equation. And finally, the total charging reactive power of the cable systems can be calculated as 678.5 kilovolt amp kilowatt megawatt, sorry. So this example illustrates the effect of cable capacitance on charging current and reactive power in underground transmission systems. This is another example. I have just 7 slides left, so can I will this link will be automatically closed. Let me uh, let me just stop.